Alright, YouTube, so finally we're getting to Schwarzschild metric. Well, I don't know about you, but I'm excited. Well, anyway, so let's start. So, once again, let's start with special relativity. This is the metric used in minkowski space, right? So it's -1, 1, 1. I'm just going to change everything into spherical coordinate. So that's why I have x set to equal to r sine phi cosine theta. It's just a spherical coordinate system, right? You remember if this is the radius, this is theta, and over here this is phi. So so the x coordinate will be just here cosine. This is sine theta, then times cosine phi, and then times r, and that give you x. Okay, so now let's take the derivative. So take the derivative of dx with respect. So dx with respect to dr give you this. Dx with respect to d theta give you this. Dx with respect to phi give you this. And here similarly with y. If you have dy here, take derivative with respect to r, theta, phi. And similarly here, so you get dx, dy, dz, and square it. So the calculation will be very tedious. You can see that if you square this, you get 1, 2, 3, 3. You get 9 more elements. A lot of them goes to 0. The only ones that remain, if you trust me, is the dr squared. dr squared, d theta squared, d phi squared, and this is what you get. So this is minkowski line element in spherical coordinate. Here as r squared d omega squared. So this is, and now we're gonna modify this to take account curvature. Remember, we've been dealing with special relativity. After this point, everything is special relativity. We're going to start taking account into curvature, but still preserving the spherical symmetric aspect of it. And Schwarzschild is the one who did this, so he this way, and solving Einstein fields equation, which is it's very complicated. And what he got was those two variables become those. So m is the mass of a star, r is the radius of the star, and now the last part, solving the motion of a free falling particle in Schwarzschild geometry. Last time when we were doing nearly flat geometry, we were able we solved the geodesic equation. We got some conserved quantity. Similarly, you know, if you do the same, which could be, I mean, which could be very complicated. I'm not gonna do it. Well, this is what you get. Tau is the proper time. T is the coordinate time. The time tau is the time that the particle carries with him. So imagine the particle being a person. He has a watch on his wrist. As he falls into a black hole, the proper time is the one that's not moving. So that's the coordinate time. And here the one is half, one is t. And let's see what happens when r equal to m. If we set r equal to 2m, that's the, well, let's see what happens. So tau 2m equals to, so that's tau, right? And let's see what's t. Okay, so this is finite, but here this is infinity. So this is infinity. So tau equals finite and t equals infinite. So what does this mean? Well, it means when a person falls into a black hole at r equal to 2m, the proper time he records is finite, but our time, the observer's time, becomes infinite, which means we will never see him fall into the black hole, which is r equal to m, but he does fall into the black hole. So that means pretty much he freezes. No, it's the Schwarzschild boundary. So this is this is one amazing aspect of general relativity. So